Chapter 12 K-means clustering. In this section, I will explain K-means clustering, which is the most popular clustering algorithm. K-means clustering is a type of distance-based clustering. It quantifies distance by Euclidean distance. K-means clustering is a non-hierarchical clustering that divides data into K clusters based on the average of each cluster. Here, K is the number of clusters that we, as an analyst, need to determine beforehand. K-means clustering is a distance-based clustering, so similarity is quantified by distance. So, in K-means clustering, close data points are regarded as similar and grouped into a same cluster. K-means clustering explores a pattern that minimizes the total sum of distance between each data point and the centroid in each cluster. Centroid is the center point of the cluster, defined as the average of each data point's coordinates. Let me explain centroid in a bit detail. Centroid is the point at the center of a cluster. It is the average of coordinates of data points that belong to a same cluster. An average of coordinate is the combination of coordinates averaged for each axis. Let's look at an example. Here, we have three data points, A, B, and C. And these are their coordinates. In this case, the average of x coordinate can be computed in this way. It is 3. And the average of y coordinate can be computed in this way. It is 6. So, the average coordinate is 3, 6. It is the centroid. At the beginning of the cluster analysis, we do not know where is the centroid. So, in K-means clustering, we assign the tentative centroid in an arbitrary place. Then, compute the distance between the tentative centroid and each data point, and create some clusters. In most cases, we cannot find optimal clustering in the first trial. That is, the first clustering result may not minimize within cluster distances and maximize between cluster distances. So, we need to adjust the place of the centroid and recreate clusters. Repeating this process, K-means will find the optimal clustering. Let's see the process of how K-means algorithm identifies clusters. First, determine the number of clusters, K, and place K tentative centroids on an arbitrary spot. In this example, K is 2. How to determine K will be explained in the following slides. We can place the tentative centroids anywhere. We do not need to deliberate where we should place them. Second, create two clusters by grouping each data point into the nearest tentative centroid. We have two tentative clusters. As we can see, the tentative centroids are not the center of each cluster. So, in the third step, move the tentative centroid to the center of each tentative cluster. We can identify the center by averaging the coordinates of each data point in a cluster. Now, the centroid is the center of each cluster, but for some of the data points, the cluster's centroid becomes more distant than another tentative centroid. So, in the fourth step, regroup each data point to the nearest tentative centroid and reorganize clusters. Then, the center of the cluster moved away from the current tentative centroids. Then, as the fifth step, move the tentative centroid to the center of each revised cluster. Repeat these steps until each centroid cannot be moved anymore, and each cluster cannot be reorganized anymore. At the point, the total sum of the distances between the centroid and each data point is minimized. That is, the optimal clustering is achieved. As I noted, in k-means clustering, first, analyst needs to determine the number of clusters, k, and place k tentative centroids in arbitrary spot. That is, in k-means clustering, the number of clusters have to be predetermined by the analyst. But clustering is analysis that explores unknown patterns in data. If k is too small, the similar cases are grouped into the same cluster, and thus the clustering is not meaningful. If k is too large, each cluster will be too small, and the clustering is meaningless for making our analysis efficient. So, how can we determine the number of clusters, k, at the beginning of the analysis? To determine the k value, we can use a metric called sum of squared errors, SSE for short. SSE is the squared sum of the distance between the centroid and each data point in a cluster. In these figures, we have two clusters, that is, k equals 2. Each dot represents data point and crosses the centroids. In the left, blue cluster consists of 6 data points. For each of these 6 blue dots, compute the Euclidean distance between the dot and the centroid. Then, compute the square of each Euclidean distance, and aggregate the square distance. It is the SSE of this cluster. Then, we compute the SSE for other clusters. The total sum of SSE can be a metric for this clustering result. A cluster should consist of similar data points. So, within a cluster, the Euclidean distances between data points should be small. Therefore, clustering with smaller SSE is desirable. In this figure, k is 2, and there are 2 clusters. The data points in the right cluster seem a little dispersed. Let's look at another case. The dataset is the same, but k is 3. There are 3 clusters. Data points concentrate around each centroid, so SSE is smaller than the previous case. So, it is a better clustering than the previous case. Next, look at the case where k is set to 6, using the same data. SSE becomes the smallest in these 3 cases. But it seems that there are too many clusters, and thus each cluster is too small. So, cluster by analysis is no better than case-by-case analysis. That is, the clustering is not so informative. In an extreme case, each cluster consists of only one data point. In such a case, SSE becomes 0. However, such clustering is meaningless because it does not find any patterns in the data. Therefore, SSE should be small, but smaller SSE is not necessarily better. So, we need a method to identify the most appropriate k value. As such a method, we can use elbow method. Let's see what the elbow method is. In elbow method, first we compute SSE for each k and plot the results, taking k value as x-coordinate and SSE as y-coordinate. For instance, When k equals 1, SSE is about 500. And when k equals 2, SSE is a little more than 300. So, if we increase k from 1 to 2, we can reduce SSE by about 200. When k equals 3, SSE further decreases and becomes around 150. But when k becomes 4, SSE further decreases, but only a little. And if we further increase k, decreases in SSE are very small. As we can see, from the case where k is 3, the decline in SSE are slowing down. It means that if we increase k from 3 to 4, we cannot decrease SSE so much. It suggests that increasing k from 3 to 4 is meaningless. That is, further increase in the number of clusters is not meaningful. In elbow method, the k value from which decrease in SSE begins to slow down should be regarded as the optimal k value. As we can see, the point looks like an elbow, and the line plot looks like an arm. It is a reason of why this method is called elbow method. Thank you for watching. Please thumbs up and subscribe to my channel.